Doing. Oh yeah. Good. Look at that.
That looks good.
Yeah. I think that'll do it. All right. So anyway, like I was saying, that's how to get into NC State. There's only really one person can do that. So
Yeah.
I think you probably deserve to go there more than Belu. So that's why I told you. Oh, let's start the recording now. Okay, now. Here we go. Okay, so. All right, maybe we can write now. Oop. So here we go. We're talking about Lie algebras. In particular, we're in chapter 4 of, where is it? Chapter 4 was it? Yeah, so solvable Lie algebras. A rough classification. All right. This is from, as you can perhaps see, Erdmann and Wildon's Introduction to Lie Algebras book. So we'll get started here. Chapter 4, first lemma 4.1. What's it say? It says that if suppose I is an ideal of L, and then L mod I, the quotient of L by I, is abelian. If and only if I contains the derived algebra so-called L prime, right? Okay, so there's the lemma 4.1. Oops, put a box around it. There we go. Now it's official. Okay, so I guess first things first, since it's been a little while, what is the derived algebra, right? Do you remember, Michael?
Off the top of my head?
No. Let's see here. We defined it back in chapter, it's either chapter 2 or chapter 1. It's where I was complaining I think there was a typo. Remember?
Yeah.
Yeah. I put a question about derivations in the quiz for linear today.
Oh, nice.
Actually, this is just full of nice linear algebra questions, you know?
Yeah.
Well, where'd you go? Where did you go? Maybe it was back. We'll find it eventually. Yeah, I guess I could use the index. That would probably be a reasonable thing to do. All right, derived algebra 1216. Okay, so here it is. Get some more markers. Probably learn how to pause that thing. Oh well. Maybe we should have to suffer through everything we suffer through. So, okay, so the L prime is equal to the commutator of L and L. And what that was what was that? It was the span of commutators. So that by the way was the span of x comma y such that x and y are both in L in this case, I mean generally speaking. So it's not just commutators, it's spans of commutators. But that's it. So let's read this lemma again. The quotient is abelian if and only if I contains the derived algebra L prime. Okay. So let's see here. Here's the proof. Oh, wonderful. I seem to have my cough again. I don't think it's as bad as last semester, but yeah, it's not good either. I'm kind of excited about this format. This could be a good format. Well, I'm going to leave this like that.
Don't take it apart.
Yeah. Like I said, I'm going to build a Lego stand.
Yeah.
Yeah. Hey, wait a minute. Maybe I should make the engineers build me one.
There you go.
Let's see here. Proof. Alright, so what does it mean for L mod I to be a billion? What does that mean? That's equivalent to saying what? The coset x plus I, commutator of the coset y plus I is just equal to, well, that's equal to, of course, by definition, that's the commutator of brackets of x and y. I shouldn't say commutator, I should say bracket, because commutator is a specific choice of bracket. So I really shouldn't say commutator. But to say it's a billion would mean that xy is 0. In other words, the coset x plus y plus I is actually just equal to I again, right? The subspace I forms the 0 for the quotient, right? So that's that. All right. So what's the deal? So basically we need what? In other words, that is what? xy is an element of I, right? Now what does he say? He says I is a subspace of L, right? We assume that I is a subspace, so we're saying at the start of all this we assume that I is a subspace. I mean, he actually assumes that I is an ideal, right? But this calculation, we're just assuming that I think we have to assume I is an ideal in order to form the quotient, actually, right?
Yeah.
Yeah, so.
Yeah.
But if it's an ideal, it's certainly a subspace. Excuse me. So what do we need? We need that the we need that the bracket of x and y is contained in I, right? But what was? But certainly. So I'm trying to prove what now? So let's see here. I guess he's giving an if and only if proof, right?
Mm-hmm.
L is abelian if and only if this is equal, right?
Mm-hmm.
But then this is true if and only if what? He's saying that's true if and only if L prime is a subset of I, right? I contains the derived subalgebra. So if we can convince ourselves that what I'm about to underline in orange is the same as the thing I just wrote, then we'd be done, right?
Yes.
Sorry, I'm going so slow. Combination of tiredness and ignorance. Some sort of superposition of those two things. Let's see here. So, yeah. But L prime is just, the span of commutators, right? So to say that L prime is a subset of I, this, if we unravel it, is to say that certainly the commutator of any two pair of things in L is in the derived subalgebra.
Right.
So certainly x prime is an element of L prime, right? So if L prime is a subset of I, right, then that implies that xy is an element of I. Which is what we need.
Yep.
Yeah, so saying the derived subalgebra is a subset of the ideal forces the commutator of things in the ideal to once more and be in the ideal. Which makes the quotient be abelian. Which is perhaps the more interesting thing, right?
Yep.
Okay. All right, moving along. All right, so he says, this lemma tells us the derived subalgebra is the smallest ideal of L with an abelian quotient. Why would that be? Because if you go smaller,
It's
then
not contained.
yeah, if you go smaller, then you don't necessarily have that the commutator of two things in that smaller ideal
Right.
is once more again and once more in the ideal. By the same argument, the derived algebra L prime itself has the smallest ideal whose quotient is abelian. All right. Namely the derived algebra of L prime, which we shall denote L2 and so on. And so we define the derived series of L to be the terms as follows. So this is like, likewise, if you look at L prime itself has the smallest, what that means. He says smallest. Smallest ideal of L with an abelian quotient has a smallest ideal, which gives, let's call that ideal J for a second, which gives L prime mod J abelian, all right? And his point is the same argument that we just went through says that you should use J basically is L prime, right? And so a pretty good notation for that obviously is L2. And we use brackets, well, not bracket, parentheses too, right? So this brings us to the definition, the so-called derived series. We have L1 is L prime, and Lk for k greater than or equal to 1 is equal to, of course, this notation being consistent with L of 0 being L itself, Lk minus 1, comma L k minus 1 for k greater than or equal to 2. I should say, yeah. Over here, I suppose we defined L prime was LL, right?
Mm-hmm.
So if you understood L to be L sub 0, you could think of this formula still making sense for the one case.
Yeah.
You might notice that these form a series in the following sense. They're nested. L contains L1, which contains L contains L1, which contains L2, which contains L3, and so forth, right? That contains Lk, and so forth, and so forth, and so forth. Now, what happens at the end of that, it can't go on forever, right? If it either has to stabilize or something. I mean, we can't have it stabilize in the sense that Lk is equal to Lk plus 1 and so forth and so on. If we're working with a finite dimensional vector space, we only got so far to go. That brings us to our definition of solvable. So here, this was just definition of the derived series. So, L is solvable if what? If for some m greater than or equal to 1, we have the derived series Lm equals to 0. So definition of solvable is that. All right. So he reminds us at this point that I suppose that's page 1 for the sake of reference. If I'm going to scan these monstrosities later. Ah! There we go. Here's what he says. He says the Heisenberg algebra is solvable. Heisenberg was... What was that one? I'm trying to remember. Let's see here.
Is it two-dimensional or one-dimensional?
It was two-dimensional. Let's see, it was discussed back in section 3.2.1. It was the... He said Z is defined to be the bracket of F and G, and was it? Yeah, it was three-dimensional, and it had a it had a one-dimensional derived algebra, and it was contained in the center val. It's his basis FGZ, where the bracket of F and G is Z, and Z lies in the center. So that was it. Of course, if Z is in the center, that means that Z with F and G with Z are both 0. So this is the only non-trivial bracket, I believe. Yep. And for example, you can build it with the matrix units E12, E23, E13, which is like 0, 0, 0, 1, 0, 0, 0, 0, 0, all zeros until 1 in the last spot in the second row, then zeros, and then 2 rows of zeros, and then 1, 0, 0. So these matrix units, yeah. Okay. Hee hee. That's kind of nice.
Yeah.
Excuse me. All right, so the Heisenberg algebra is solvable because the L2, right, for Heisenberg, we just said Heisenberg was the span of F, G, and Z, with the only non-trivial bracket being F and G, giving us back Z. So the if I may call this L, like a civilized human being, for the Lie algebra, and then so the L prime, of course, is the span of Z, because that's the only thing, and so then L prime prime, or L2, would just be 0. So this is solvable. Furthermore, the classification of two-dimensional algebras back in section 3.1 shows that any two-dimensional Lie algebra is solvable. That's not terribly surprising, because the commutator of a vector in itself is, the bracket of any vector in itself must be 0. I keep saying commutator. What can I tell you? I live in the world of matrices too much. On the other hand, if you look at SL2C, right, which was a three-dimensional one, right, the special linear algebra of 2x2 matrices over the complex numbers, we saw in exercise 2.2 that, in fact, its derived algebra was just itself again. And so that's example 1. Example 2, SL2C, little SL2C, right, which we could build. Let's see, what was a convenient basis for that? It's kind of an important example. Oh, come on, you silly thing. Where'd you go? Where'd it go? There's a whole book written just about representations of SL2C. It's an important case. Alright, come on. Out with it. Where's that stupid thing? There's notation I'd like to remind you. There's like E, F, and G here, I think, is a standard notation. I would like to reproduce that here before we go on. Do you remember?
Mm-mm.
Ah, curses. Page 3. All right. Oh. Let's try page 33. What he says on page 3 is still very matrix centered. Yeah, page 33 is a big picture thing. I want something more slick. Oh, curses. Bear with me here for a minute. Page 129. Aha. Here we talk about SL plus 1, comma C. I'm really interested in L equal to 1. So he has... I think it's this. I think it's the span of E, F, and H. And in this one, you have the bracket of E and F equal to H, which would look just like the Heisenberg, except we also have H. I believe we also have H and E equal to E again, if I'm reading this correct, 2E. And I think we also get H and F also equal to 2F, if I'm reading this correctly. Now let's see if we can't make good on that for some explicit matrices before I insist on that notation. Now, back on page 3, he said SLNF has a basis EIJ for I not equal. I mean, he basically well, he used, okay, so I got it. I think the explicit 2 by 2 matrix construction of this is just as follows. You know, I used to know this stuff. So I believe H, we can use 1 minus 1, 0, 0. And then like E is either, I think it's 0, 1, 0, 0. And then F is 0, 0, 1, 0. Of course, these are 2 by 2 complex matrices. So for example, let's see here, what's H times E equals to what? Right, and E times H, 0, 0, minus 1, 0, right? So you put those together, and you get that the bracket of HE is equal to 2 times one of these guys, because you get minus plus, but that's exactly 2E. Likewise, you can prove that HF is 2F, and I'll do the interesting one. EF, let's see here, EF would be 1, 0, 0, 0, right? FE would be 0, 0, 0, 1. So when you look at the bracket of E and F, what do you get? You get 1, 0, 0, minus 1, otherwise known as h. Okay, so in this example, if we look at L prime, right, we have the span of basically all possible commutators, right? So you got like E and F and E and H and H and F. I mean, I think that's pretty much it in terms of distinct doubles. But of course, that's exactly the span of, well, E and F is like H. E and H is, minus 2E, and H and F is 2F. So it's not hard to see that that's exactly SL2C again. So therefore, SL2C is not solvable. And moreover, we have that the mth derived, LM is just equal to L, for all m greater than or equal to 1. So the series stabilizes to just L itself. Okay. So far so good? Good. All right. Keep losing my place. Where were we? So SL2C is not solvable. All right, so if L is solvable, then the derived series of L provides us with, quotes, an approximation of L by a finite series of ideals with abelian quotients. So an approximation in the sense that if you look at quotients in this series, it gives you some kind of information about L itself without actually studying L itself, right? So in that sense, it's an approximation. I'm not sure. Well, I'm not an abstract numerical methods kind of person, so I'm not sure. Take it for what it's worth. But this also works the other way around, he says. Here's our lemma 4.3. So, that was page dos. Here, number 2. So here we go. I guess it would probably be more helpful if I page numbered them at the start as opposed to the end where you could just find that one number, that 3 seconds of video where the number's showing. It's probably not the best format choice. Oh well. Price is right on these videos. All right, so lemma 4.3. Lemma 4.3, what we got? If L is a Lie algebra with ideals, and you have ideals, and the ideals will denote by I sub 0, I sub 1, I sub 2, so forth and so on, all the way out to the mth one, and these ideals are not just any old ideals, they are nested in the following way. L is equal to I naught, okay? And that's a subset that contains I1 rather. And I1 contains I2. And so forth and so on until you get to the m minus 1th one. And that contains IM. And IM is equal to 0. Alright, so we've got this series of ideals, each one containing the one after it. The one before it. Mm-hmm. And we also need a little bit more. We also need that the quotient of ik minus 1 by ik, if those quotients, if that is abelian, all right, for 1 less than or equal to k less than or equal to m, all right, then what? What's the punchline here? L is what? What do you think?
Solvable.
Right. So we just had we had the converse to this already, right? We said, suppose L is solvable.
Right.
Then we produced this, we showed that, first of all, L mod the derived algebra, L mod the derived algebra is abelian. And then we argued, well, if you look at the derived algebra of the derived algebra, then the derived algebra mod the derived algebra is abelian.
Right.
And this process continues. So the way we constructed the sequence of ideals, the series of ideals, was through derivation, if you like. There's nothing about derivation in this. This is just, you've got this set of ideals that has this nesting property such that the quotient of subsequent ones in the appropriate way is abelian. That's enough, that data, to prove L is solvable. Let's see how. So here's the proof. As usual, I am thieving it from Erdmann and Wildon. All right, so here's the proof. Let's see if we can understand it. We shall show that Lk is contained in Ik for k between 1 and m. And then putting k equals to m will then give Lm as 0. All right, so he says we shall show that L, the derived, now he's looking at derived algebra. He's like, okay, well, you started with this, bunch of ideals, but now he's going to relate them to the derived algebra, okay? He says he's going to show that Ik is contained in Ik, not Ik, Lk, the kth derived algebra, right? He's going to say that is contained in Ik for k equals to 1, 2, all the way out to m, right?
Yep.
And then we already have the data that when k is equal to 0, that k between 1 and m, putting k equal to m, oh, it's the mth one that's 0. I'm an idiot. Duh, right here. So when we get to m, we get 0. Okay. Okay, so here we go. He says, since L mod I1 is abelian, right? We assume that. Well, L mod I1 is I naught mod I1, right? Which is assumed to be abelian.
Right. So I1 contains
So what you say that implies what?
I1 contains L prime,
Right. Why do we know that?
the first lemma.
Right. By lemma 4.1. Oh yeah, we did just get done proving that.
Yeah.
Sadness. Okay, so now we use induction. Suppose that the k minus 1th derived algebra is contained in Ik minus 1, okay?
Mm-hmm.
Where k is greater than or equal to 2. The Lie algebra Ik minus 1 mod Ik is abelian. We assume that. So then what? Now we're going to use lemma 4.1 again, applied to Ik minus 1. So apply lemma 4.1 to, where did it go? Ik minus 1, what do I do there? So that would say what? Lemma 4.1 would say Ik minus 1 prime is what? is a subset of IK, right? Because we know that the quotient of IK minus 1 by IK is abelian. So that means that the derived algebra of IK minus 1 must fit inside IK. Right?
Mm-hmm.
But our induction step was to suppose that, well, LK minus 1, well, let's see here, but what do we know? Sorry, I'm getting lost here for a second here. I can put this in, therefore, let me just write that out again. The IK minus 1, I don't know if this really adds anything. So we have that. He said, but LK minus 1 is contained in IK minus 1 by our induction hypothesis. So we have that. So I guess he's just going back to the induction hypothesis and writing it out again. So we have LK is equal to, of course, LK minus 1, LK minus 1 bracket, which is a subset of IK minus 1, yeah, IK minus 1. How do I know that? That was the induction hypothesis, right?
Right. Yep.
And then this subset of IK. Hence, the kth derived algebra is a subset of IK. And so, as he says, let k equal to m, and we have, L, m is a subset of I, m, but IM was assumed to be 0. So therefore L is solvable, as claimed. Alright, so this proof shows that LK non-zero, then IK is also non-zero. Hence, the derived series may be thought of as the fastest descending series whose successive quotients are abelian. Lie algebra homomorphisms are linear maps that preserve Lie brackets. All right, so one would also expect that they preserve derived series. And here's an exercise, basically to that effect. What's the exercise say? Should we do this exercise here and now,
Sure.
so that we can take that away from Belu?
Yeah.
She won't have a chance to rub that in your face. Be like, haha, I already did the exercise before you. Well, ha, 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 ha. That's right. That'll show her frivolous, needless tourism of a ancient dead city that no one cares about. Let's see here, exercise 4.1. Alright, so exercise says, suppose we got phi L1 to L2, a surjective homomorphism. Homomorphism of Lie algebras, of course. What else are we going to do? Homomorphism of, come on, of course it's of Lie algebras. Anyway, show that phi, oh man, I forgot to say linear transformation was linear, one of the linear algebra homeworks lately, and oh, they were just in the tither about that. I was like, just email me, people. Don't suffer. Don't spend hours on it. He said, I spend hours on it. I'm like, why? Why would you do that with your time? Like, just email me. L1. So here's the way it works, supposedly. This exercise suggests the property of being solvable is inherited by various constructions. And then it gives a lemma to make good on that claim, but let's see if we can prove this exercise first. Okay, so let's see your proof. So we know that what we're given, right, is that phi of x bracket y is equal to phi of x bracket phi of y. That's what it means for it to be a homomorphism.
Right.
And we also know that,
It's surjective.
yeah, so for each y in L2, there exists x in L1 such that phi of x is equal to y. I mean, that's also something we know.
Mm-hmm.
And we're trying to show that the image...
Do we do induction on K?
Yeah, so let's begin with k. So consider k equal to 1. Yeah, good idea. Induction on k is a good idea. K equals 1. So what's L1? L1
So it would be phi
of 1 is L prime, right?
Right.
So that's the span of x and y, L1 prime, such that x and y are in L1, right? But of course, so you're looking at the image of that, right? So you look at the image of that, yeah.
You do this because it's surjective. It's a homomorphism. Since it's surjective, this is L2.
Exactly.
Okay.
Yeah, yeah. Let me suffer through this point notation, then I'll write what you wrote down. I like it. It's good. So, yeah, this marker's, it's too yucky. Yeah, what you wrote was good. So phi of L1 prime would be the span of the images of these things, right? Which, as you said, homomorphism. And,
It's surjective.
right. But as x and y go over L1, these brackets have to hit everything. So, I mean, this is the same as saying the span of, say, you know, I mean, in this notation, I guess I would just write this. And it's logical to replace that with that because the images phi of x and phi of y hit everything in L2 because phi is surjective. And then, of course, this is just the bracket of arbitrary things in L2, so this is exactly L2 prime. That's the k equals 1 case. Now, what Michael wrote, I like. So you wrote, what was it? Let me just copy it down. Oh, hey. Michael wrote this. Oh, excuse me. Oh, I cannot laugh. Let me try that again. So you have phi of L1 prime. And the way you thought about that's not bad at all. I mean, it's really good, actually. So that's actually usually working with sets instead of points, which is not bad. L1 prime is the bracket of L1 and L1. But then to say phi is a homomorphism is to say that this is equal to phi of L1, phi of L1. And then that is surjective, so that's L2, which is, by the way, L2 prime. And so this argument up here is just kind of some of the details of that.
Yeah.
Anyway, of course I do not allow these kinds of pointless arguments in linear algebra because then there's like nothing to prove.
Yeah.
Which goes back to my point. Linear algebra is easy. But anyway, I'm trying to sell it. Students aren't buying. So, oh well. Oh, induction then, right? So suppose inductively then. What are we supposed to suppose inductively? That phi of L1k is equal to L2k for some, let's say for k equal to n, all right? And let's look at n plus 1. So look at phi of, and I'll use your notation. So phi of L1 of n plus 1, right, is equal to what? It's equal to phi of bracket L1 of n with L1 of n, right? Which is, by the homomorphism, you know, if something's a homomorphism for the whole Lie algebra, it's certainly a homomorphism on subspaces as well. In other words, we're just looking at a restriction to a subset, so they still have the homomorphism property. Anyway, so that's phi of L1 of n, comma phi of L1 of n, which by the induction step is equal to L2 of n, right? Comma L2 of n, which by the way is exactly the definition of L2 n plus 1. So thus, by proof by mathematical induction, PMI, this exercise 4.1 is done. Aha! We finished that homework before Belu. She can't take that back from us. We are the winner. She's the loser. Oh yeah, let's see here, 5. Number 5. Now that brings us to that all-important lemma 4.4. Lemma 4.4 says, let L be a Lie algebra then I'm just going to find I like to use blue for theorems, but my blue markers are all kind of sketchy. I wish I'd get to be the after-school sale again. I need to buy some more markers. Not that my markers are run out; they're just kind of getting. Thing is, I leave them around the house, then the kids get them, and they do things to them. Mostly coloring, but coloring is the death of my markers. If L is solvable, then what? Then every subalgebra, what's the subalgebra of a Lie algebra? Some people would say sub-Lie algebra. And every homomorphic image of L is solvable. So subalgebra would just be a subspace which is a Lie algebra in its own right.
Yeah.
Which is of course a weaker condition than the ideal, which has to have, as Dr. Sperano says, uber closure. So no uber closure, just self-closure. Am I right?
Yeah.
So just worry about what you think. Don't worry about what other people think. In other words, I see here.
Yeah.
Good way to live. All right. Suppose L has an ideal I such that I and L mod I are solvable. All right, then L is solvable. So yeah, I hope I'm recording. Yeah, I'm recording good. Oh, and then part C. If I and, oh, let me see, what did part B say? If L is an ideal I, such that I and the quotient L with I are solvable, then L is solvable. Oh. Hey, that's pretty cool. So if you know the quotient and an ideal are solvable, that gives you that the whole space is solvable. Neat. See. If I and J are solvable ideals, of L, then I plus J, remember, which is formed from the span of things from I and J, is a solvable ideal of L. Okay, so that's lemma 4.4. All right.
It's 1:05 p.m.
Silence, woman. Let's see. All right. Just push on ahead here. Oh, the proof. I suppose I should share with us the proof. Yes. How do we prove it? The proof of part A. What do you think? Let's suppose L1 a subalgebra of L, right? He says it's clear that the kth derived subalgebra of L1 is a subset of the kth derived algebra of L. Observe L1 of K is a subset of L of K. Now I'm just going to stop right there and make sure that that makes sense. Right? Does that make sense? So, like for example, L1 prime is L1 with L1, right? Which of course is a subset of L1, right? But also, you know, the fact that L1 is a subset of L implies that, you know, the bracket of L1 with L1 is a subset of L with L, right? We use that. We have used this. We used this in the last proof. That subset extends to bracket.
Yep.
Like subset of a set means that the
Derived is the set.
yeah. There's probably something there to prove that. I'm not sure we actually proved that anywhere yet, but it shouldn't be too hard to prove this. But anyway, of course that's L1. Yeah. And so a similar argument would hold for this, like, you know, basically L1K is a subset of LK, which would be LK plus 1, you know. And so anyways, this you can keep going up the chain and get that. So anyway, let me just, in other words, like we said, observe that the kth derived subseries. So the algebra is a subset of the kth derived algebra of the whole space. But then what? L was solvable, right? So that means that yeah, there exists M greater than or equal to, is it 0 or 1? I think 1. 0, okay.
Yeah, it's 0.
I guess that's good. That allows for abelian algebras to be solvable. Because if M equals 0, that means that the derived algebra is 0, which means the algebra is abelian. So M greater than or equal to 0, such that Lm is equal to 0, but that implies that L1, so you got a subset of 0, but, right. I guess I'm feeling guilty. I should really say set containing 0.
Yeah, that's what I've been doing.
That's good.
Yeah.
That's good.
I felt bad on the first one.
Yeah, I think he slipped that past me there somewhere, didn't he? So therefore, L1 solvable. Okay. But L1 was an arbitrary subalgebra, so there you go. That's every subalgebra. And the homomorphic image probably comes from that,
What we just did.
the exercise we just did.
Yeah.
So homomorphic image of an, so we have phi of, so if we look at phi of L1, which would be, homomorphic image, phi of L though, right? Homomorphic image of L, so I have to take phi of L.
It won't be quite the same because the exercise was surjective. We'll have subsets instead of equals.
Oh.
But it would be very similar, I feel like.
Every homomorphic image of L. Well, we can always but we can always define we can always take the homomorphism and just redefine the codomain to be its image and make it a surjection.
I mean, yeah.
Yes. Yeah, so let phi go from L to phi of L.
Yeah.
Okay, so let phi be a mapping from L to phi of L. Aha, surjection. Take that. No. Yeah, and if so it's a homomorphism, then let's see, phi L of M was equal to phi of Lm, right? That was exercise 4.3, but that's phi of 0, which is 0. Sorry, set containing 0. Set containing 0. It is kind of a drag to write that.
Yeah.
What's the harm in saying 0 is the 0 set? It's just one more degeneracy for 0.
Yeah.
Although I can't strike my usual holier than thou. How dare you not understand linear algebra for linear algebra if I do that, so I do like to take my points. Let's see here. Can't let the students feel too good about themselves,
Yeah.
Gonna knock them back down. Here, no. Especially the Chinese. Oh, okay, so there you go, that's part A. Part B. For the second part, he says apply exercise 4.1. Oh, yeah, that was exercise 4.1 that we did, not 4.3. All right, so here's part B. Not sure that's actually readable. Maybe, maybe not. Probably not. I guess I can behave. So for part B, what we're trying to prove, if, oops, shouldn't bump that thing. Trying to prove if L has an ideal such that I and, so we know that I and L mod I are solvable, right? So let's see, we're given that I of M is 0. I'm going to use 0 instead of the set containing 0. You can hopefully forgive me. And L mod I